Okay, welcome back, ladies and gentlemen. Our first speaker after the recess is Ron Majors, formerly from Agilent, but retired, and now at Advanstar LCGC. He's also on the governing board of the Chromatography Forum. So as the title today is The Changing Relationship Between the Column and the Instrument in Modern HPLC and UHPLC. Okay, Ron. Thank you.
Thank you, Mary Ellen. I'd like to add my congratulations to Dr. Worth. And I first met Mary when she was down at Delaware, just down the road from where we worked. And she got into self-assembled monolayers and then started to use spectroscopy to look at surfaces. And she saw the light going away from spectroscopy into chromatography. And I also admire the way you support and are a proponent of women in analytical chemistry and chromatography. I had many discussions with Phyllis Brown, who was really the first woman who was in a male-dominated HPLC in the early days in the late 60s and early 70s, and she tells me a lot of horror stories about how she was treated. But in her work, a lot went unrecognized because of just the climate at the time. So, okay, I'm going to talk about columns. This is an area that I've followed in a lot of my career. And this is basically an outline. I'm going to try to stick to it if I can. But I'm going to talk about some of the newer particles. Some of you in the audience, of course, are quite familiar probably with what's been going on in the HPLC field. In the last 5, 6, 7 years, it's been a very exciting time if you work in column technology because a lot of things have happened. There were so many years that we went on where, 5 and 3 micron particles were basically pretty commonplace, and pressures were all 6,000 psi, and not a lot of excitement was going on like it was in the early days of LC when columns were really developing. So anyway, I'm going to talk about some of the particles. If you have not heard about the superficially porous particles, I introduce you to those. Then we'll talk about how do you compare these different types of particles and which might be the best to do chromatography. And to really not make a big detective story out of it, I was just talking to Mike McGinley about this. The world is going over to superficially porous particles if you haven't already seen that. And I'm going to show you why. Then at the end, since my title does have some instrumentation in it, I am going to talk about some of the instrumental aspects of these newer columns and how at times the instruments are not keeping up with the columns and other times the columns aren't keeping up with the instruments. So this is a chart I've been keeping track of from the early days and up till the present. And basically, what it shows you is the year of introduction of some of these column materials. And I was around in the early days of HPLC in the late 60s, and probably the molecular packings, not probably, the molecular packings and the UV detector really are the two driving forces that made HPLC break away from the old days of column chromatography. And this glass bead based product was just that. It was a glass bead with a silica gel. Out of the way, Tom. Plug it. This was a glass bead about 50 microns in diameter. It's nothing like the superficially porous packings of today. But on the outside, on the periphery, you had this thin film of silica gel and oftentimes ion exchange resin. This is where all your separations took place. So needless to say, the sample capacity for these molecular packings was very low. In fact, you couldn't really use them for prep chromatography. But the efficiency was dramatically higher than it was for the old irregularly shaped silicas and aluminas that were used in open column work. But in the early 70s, those microparticulate packings were able to be sized. They took TLC packings and sized them into smaller fractions, like 5 to 10 microns and so on. And then later on, as DuPont and others like the Zorbacs and the Rockland technology, they became spherical versus irregular. And after that, the molecular packings really kind of went away and went to sleep for a couple decades. But again, you'll notice as the particle sizes started to decrease, we first had the 10 microns in the 70s, the 5 microns in the 80s, the 3 microns in the 90s, and then later on, of course, we went to even sub 3 and sub 2. And the porous particles get smaller and smaller and smaller, and nowadays they're all, for the most part, below 2 microns. But every once in a while, this molecular idea would raise its head. First in 1999, when Jack Kirkland, who was actually one of the fathers of the early molecular packings, actually came out with what was called PoreShell 300, and it was mainly used for proteins with wide pores. And again, a few years later, about 10 years later maybe, or 8 years later, the molecular packings in the 2.7, the sub 3 micron molecular packings came into being, and this is where all the action is today. And we're going to show you some of the highlights of that. So why are people looking at new packings all the time, and why companies looking at it besides trying to sell more columns? It's because the users are demanding it. So nowadays, everybody wants speed. People want to do more with less. They want to do things faster, lower cost, and so on. This has driven the columns market and the instrument market to some degree. So nowadays, short columns are in vogue with small porous, totally porous, or superficially porous particles. Sometimes longer ones are used, but most of the time you'll see a lot of separations that used to be done on 25 centimeter columns can be done on 50 millimeter columns, and that brings a lot of advantages to the end user. High flow rates are in vogue now, mainly because some of these Van Diemter curves shift to the right as you go to the smaller and smaller particles. So high flow rates are in to get better efficiency. If you try to run some of these columns at 1 milliliter a minute, you'd be used to running on your 4.65 micron columns, you're going to actually lose efficiency that you'd gain by going to a higher flow rate. Things like gradients now are what we call ballistic. I mean, they're going from 0 to 100%, or maybe from 10 to 90% in 2 minutes, 1 minute, resulting in very fast separations by gradient. Elevated temperatures are in vogue as some of the columns now can take temperatures well in excess of 60 degrees. And then, of course, HPLC systems, now called UHPLC, was just really another name for LC. But everybody's tried to pass it off as something new and different, and mainly by the instrument companies trying to sell you an upgrade for your existing LCs. And we'll talk about that a little bit later. Okay, well, this set of packing cartoons here sort of tells the tale of where things have gone in the past several years. Used to be 5 microns that were in vogue, and now the sub 2 microns, 1.8, 1.7, 1.6, down to 1.5 for totally porous. Jack introduced in 1999, 2000, the molecular packing, which was called PoreShell. The advantage here, and this was made for large molecules, and this was really a boon because your mass transfer in the stationary phase was definitely improved by going to these molecular packings. The protein would come down the column, and instead of diffusing all the way in the center and all the way back out again, which would broaden it, and especially at high flow rates, these molecular packings, superficial porous packings, now all of a sudden limited the diffusion distance. Now, when you go to the smaller superficially porous packings of, say, sub 3 and sub 2, it turns out that the mass transfer is not the driving force in the efficiency of these newer packings, and I'll show you in a minute maybe why. Now, this is I've been keeping a track of all the new commercial 2 micron and sub 2 micron particles, and you can see now that I think there's a total maybe of 26 or 25 or something like that. These have been introduced in the past, say, 5 to 10 years, but almost every company now in the chromatography business and the packings business has a sub 2 micron particle. But interestingly enough, I just added to this table, I just finished my Pittcon articles. Every year I do 2 articles on new columns and sample prep stuff at Pittcon. Only one company introduced a sub 2 micron, whereas 3 years ago they were being introduced right and left. Because the action is not in this domain anymore, believe it or not, it's in the superficially porous domain. So let's talk about superficially porous particles. I will talk about Agilent particles because that's who I used to work with, and they graciously let me use the slides. I can't just take the slides and use them anymore like I used to be able to do. But but I want to talk about the superficially porous, and there's a lot of superficially porous out there. They were known in the old days as molecular porous layer beads or superficially porous. I like to stick with the old ways, so I call them superficially porous, or SPP abbreviation. But they're called fused core, core shell, solid core, shell particles, porous shell. I think there's probably more names for them, but they're all basically the same sort of domain or same sort of particle. They all have a solid core, obviously, and they have a shell. Some shells are thicker, some are thinner, some particle sizes are bigger, some are smaller. For a 2.7, which is this one from Agilent, The efficiency is, and I'll show you some results in a minute, the efficiency is basically almost the same, plus or minus, as a sub 2, but the pressure is roughly half. So they can tell you right there, if you have the same efficiency at half the pressure, you're going to be more pleased because you don't have to push your pump to these 1,000 bar and 1,200 bar limits. You can sometimes even use your old LC systems, your 400 bar systems, to work with some of these packings. But you still have to take care of your instrumental considerations, and we'll talk about that later. Now, one thing that's nice about these, the ones that are sub 3, 2.7, 2.6, and so on, is you can use a 2-micron frit. That doesn't sound like, well, big deal. That's the same frit you use on your 5-micron and your 3-micron columns. When you go to the sub 2-micron totally porous columns, because the particle size distribution is such, you have to use a much smaller frit. And these smaller porosity frits are much more prone to plugging. You know, and so you hear a plugging with these sub 2-micron columns is a problem. And if you don't do a good job of cleaning up your samples, then indeed you can plug those columns. And sometimes you can reverse the column and flush them out. Other times you can't. So that's a big advantage of some of these newer types of packings. So how are these things made? They're all sort of made the same way, whether it's an Agilent or a Waters or a Phenomenix or so on. You make a solid core. You apply the shell, silica gel most likely, or there's been other inorganic substrates or shells, but silica is still the most popular, and then you put on a bonded phase. So the process that's used to make these things is called the Stober process. It's pretty well known. You can make very spherical and very narrow particle size distribution particles. They're particles, but they're the base particle. They're not the final particle you'd pack in a column and use. But they have, usually they're sub 2 micron, even smaller for some of them. But they're very smooth surface. You can see here. There's no, of course, any packing on the outside yet or any silica on the outside. Very tight distribution. And this leads to some advantages when they're put into columns. Now, the coating process is done several ways. The original process for Porous Shell 300 was what we call an Aufbau process. You build up layers, like as many as 10 layers of, say, 0.2 microns per layer, for example, something like that, or maybe smaller. Anyway, you build it up. The new process that Agilent developed does it in one step, so it's a little bit more easier to control than trying to do a multi-layer process. But you see, these particles actually have a fairly rough surface, and that's been one of the theories proposed by Professor Guillochon and some others, that maybe the efficiency of these sub 2 microns is not just only the narrow particle size distribution, but can also be the surface roughness. It's still out. The jury's still out on that, though. Okay, well, so look at these particles. The red are a Porous Shell 120. The black is 5 microns, 3 microns, and the blue is 1.8 microns. You can see definitely they have a narrow particle size distribution than the others. But there's been a lot of studies done now. In fact, I don't know if Dick Henry's in the audience, but Dick just wrote a paper. We're doing a special issue on column technology for April's LCGC. And Dick wrote a really nice paper on particle size distribution studies that he has done with some of the people at Sapelco. And in fact, he's done some work where they're using porous particles now that are monodisperse, and they're like 1.9 plus or minus 0. And these have actually brought some interesting efficiency to the totally porous particles without the high pressure drop. Because remember, the pressure drop is 1 over dP squared. So if you have a wide distribution, then the small particles in that distribution are going to cause a lot more pressure than the particles in the middle. So if you have monodisperse, you should have a lower pressure drop and maybe even some better efficiency, although that's not been really proven yet. Okay, so anyway, they're narrow, about 30%, 20% narrower than a porous particle. Why do these things work so well? Well, you actually improve all 3 terms in the Van Diemter. The A term, which is the eddy diffusion term, the B term, which is longitudinal, and the C term, which is the mass transfer. So normally in the older particles, mass transfer dominated these type of packings. Here, the mass transfer term for small molecules is actually quite small. Whereas for large molecules, it still is one of the dominant players in the mass transfer. Anyway, so the biggest thought now in the theoreticians is that the A term is the one that really gives you, the SPP particles really give you the lower A term because of the nice particle size distribution. But again, Guillochon and Gritty, who have done the most studies on this, indicate that there may be some other contributions from things like the surface roughness. And even the B term has some advantages for the superficially porous particles. Attached to bonded phase, today, 2 years ago, everybody was just introducing their first C18, C8s, and the normal stuff. But nowadays, there's just about as many different chemistries available on the superficially porous as there are on the totally porous packing. So that's one thing that's happened. Now, this is the list of companies now, and there's another slide that shows the ones that are just introducing here at Pittcon. But these are the companies who have already introduced in the past, say, 3 to 5 years, these superficially porous particles. I'm not going to get into every one of them. There's different particle sizes, different shell thicknesses, and so on. Some are for proteins, some are for peptides. The larger, like the 160s, would be for peptide chemistry, or larger pore sizes. There's as small as like 1.3 and as large as 5. So the world now is going to actually trying to substitute the 5-micron superficially porous particles for the regular 5-micron totally porous particles that we've been using for years. And with the pressure drops being lower, and therefore you can use longer columns and gain some advantages there. So there's lots going on. These are the companies they introduced last year or two. These are the companies that have new products here at Pittcon for the very first time. And so the total number of companies that are going in the superficially porous world are almost equal to the number of companies who are doing totally porous particles. And this is where all the action is. So you're going to see a lot more of these superficially porous particles coming out over the next few years as new companies come into the marketplace and as new phases are developed. Normally when a company introduces a new particle, they don't have 9 or 10 different phases. They kind of introduce 2 or 3 at a time, and then 2 or 3 next year, and so on. It does take time in R&D to develop these products, Okay, so let's kind of look at these, and I'm going to run through these fairly fast because the end result is that the particles are almost the same except for the pressure drop, basically what it boils down to. So efficiency-wise, this is what sold everybody on UHPLC, was taking a separation that was done on an old column, and then by decreasing the particle size, decreasing the column length, you basically do the same separation, basically the same resolution, in a much faster time because the columns are shorter, okay? Now, you do have to sometimes introduce less sample, but most of these columns are never near their overload state anyway. So these are just some xanthines. This is where, people were 3 or 4 years ago. If you get 12,000 plates on a 15-centimeter 5-micron column, you can get 12,000 plates on a 50-millimeter 1.8-micron column. Why would you want to play around with a long column like that? And that's what people are now switching over to the shorter columns. They operate at a lower pressure. You save solvent because it's shorter. You run at the same flow rate. You save analysis time, and that's where the world has gone. Typical Van Diemter curves, you'll notice that the smaller particles, they get flatter, which means you can run at 1 mil a minute or 4 mils a minute and get almost the same efficiency. But if you use a superficially porous particle, you basically can just get the same efficiency anyway. And one thing about the Van Diemter, it doesn't tell you what the pressure is. It doesn't play into the pressure equation. So you don't really know that these columns here are causing a lot more back pressure than the superficially porous particles. So here's just an example of taking an old separation on a USP method, transferring it over to a superficially porous particle, and again, you're going from 8 minutes down to 1.5 minutes, just like you did on the totally porous particles, but you see the pressure drop even on a 50-millimeter column is very, very low. So what about pressure? Well, pressure is related to a number of parameters in the chromatography world. Viscosity of the solvent, obviously you want to use isopropanol. You don't want to use isopropanol. You'd use acetonitrile, your organic solvents, lower viscosity. Column length, longer the column, more pressure. Higher the flow rate, more pressure. But the biggest factor is the particle diameter squared. So every time you have the particle diameter, your pressure goes up by a factor of 4. Okay? And this is where UHPLC came in, because all of a sudden, people went down to these 1.8, 1.7, 1.6 micron particles, and their pressures of columns that were 100 millimeter or 150 millimeters run at high flow rate, which we like to run at for these things. The pressures did get over 400 bar. So people did upgrade. Some of them maybe wish they hadn't now because they didn't have to do that with the newer particles, but they did. So why higher flow rates? You get higher peak capacity when you run a shallow gradient with the high flow rates. There's pumps out there now. I think the highest pressure pumping system is 19,000 PSI. Both of these type of columns, the sub-2s and totally porous, should be running at higher flow rates because of what I've talked about before with the Van Deemter. And you just have to be careful when the 1.8, if you get too long of a column, and I'm going to show you some examples where the pressures can get up there where you need to have that UHPLC system. One thing that's very interesting, the pressure, as I already talked about, is about twice as much for the totally porous as a 2.7 pore shell SPP. But you notice one thing about the outcome of going to these newer HPLC systems, in order to get the dead volume down, the X column volume, the gradient delay volume, you have to cut the ID of the tubing. So, this is for 0.112. Nowadays, with these high efficiency kits that are coming out for the UHPLC systems, they're going to 0.075 millimeter. Now you can imagine 0.075 is like thinner than a hair, and you're going to plug those if you happen to sneeze the wrong way. So that's one of the things that the pressures are going up just for the system alone, not even without a column present. Okay? Well, let's look at some of the trade-offs. Again, this is a totally porous, 3.5 minute separation, good resolution, higher pressure, superficially porous, same separation time, same resolution more or less, lower pressure, more of the same. With the SPP products, you can actually run longer columns and keep your 400 under 400 bars. Here's a system of looking at a 100 millimeter column, 4.6, 2.7 micron SPP, run at 2 mils a minute, generating 394 bar just below the limit of the pump. But if you have the pressure to spare and you have a UHPLC system that goes to 1200 bar, then you can do things like this, running small ID columns like a 2.1 at, this is 2 mils a minute, which is equivalent on a 4.6 of what, 4 times that, 8 mils a minute on a 4.6. And you can get separations, in a fraction of a minute where these peaks are only, a fraction of a second wide and only a few microliters in volume. Again, you can increase the flow rate on the SPP much more than you can on totally porous particles. In most cases, trying to do the same thing with a totally porous particle of the smaller particle size, your pressure is going to be about double. So that's why people are converting over. If you got a really long columns on a totally porous, now you're talking about using that 1,000 bar, that 1,200 bar pressure rating. Whereas you can generate 100,000 plates on a superficially porous particle, here putting 350 millimeter columns together and just have nominal pressure, 573 bars, doesn't even use half your pressure on some of these systems. And just more of the same. This happens to be for very long columns, 55 centimeter superficially porous, 55 centimeter totally porous, and again, it's twice the pressure for the same separation, about 100,000 plates. So you're going to generate 100,000 plates on a 1.8, 1.7, you're going to have to use a fairly long column. You can't just use a short column to get those kind of plate counts. I'd be remiss if I didn't mention monoliths. Monoliths have come alongside of the porous particles. They're about 15 years old now, but monoliths have never really taken off. Part of it is because it's a one-source product. You can't go out and buy monoliths, silica monoliths from a number of companies. There is the first generation monolith, had problems with tailing and other things. There is a newer generation monolith called Chromalith HR, product of Merck Millipore in Germany. And it does have some advantages. They have changed the macro size, meso size ratio. So these products do have a higher pressure drop. One of the advantages of the monoliths in the past is the pressure drops have been really low. The efficiency, pressure drops really low. The efficiency of the red one here was about the same as a 4-micron particle for the first generation. The second generation, the newer HR, will be equivalent to about a 2 point something or other, 2.2 or something like that. So the efficiency is better, but the pressure is higher. You can get nice separations on monoliths just like you can on sub-2s and totally in SPPs. This shows a chromolith on a fast gradient separation, nice peaks. This is a slide I got from Merck. I'm not quite sure I believe all of it, but they show a 400 bar separation on a chromolith second generation to a coarse shell particle. It didn't say whose it was, but anyway, 2.5 times lower pressure, but take it as you will. Monoliths are, I think, do have a future. Once the patent expires and other companies maybe get into monoliths. Okay, how do you compare all these different columns? Now, we've talked about pressures, we've talked about particle sizes. There's all sorts of ways you can look at these column efficiencies and pressures. The one that seems to be gaining popularity is the one called the kinetic plot. A chap named Gert Desmet, who's a professor in Belgium, sort of took the Poppy plot and modified it. It's a plot of log T0 versus log N at a certain constant pressure. And I'll show you what these things look like. They look kind of complex when you first look at them, but it's plotting T0, which is the void time, versus efficiency. So over in this domain here, you're doing fast separations where you only need maybe 1,000 or hundreds of plates at high velocities. Up here, you're using these for long separations, long separation times at low velocities. But it's really interesting to compare using this, and these lines here represent different pressure ratings. So the higher the pressure your system goes, you'd move these curves are all moved down. But on this curve, on this plot, are 3 different totally porous packings, 5, 3, and 1.7, 1.8. And then there's the monolith, which is green. And then the pink is the superficially porous particle. So what does this tell you? Well, it shows for very short lengths that the superficially porous particles are probably the best choice. But even as you go to very long separation times, very high plate counts, the monolith starts to take over. Right up in here, monolith. Unfortunately, the monoliths right now are only limited to 10 centimeters long, and they're clad in PEEK, so it can't go to higher pressures than 200 bar. Now, if Merck could develop the products that would go to high pressure with the monoliths, then for very difficult separations, and it's already been shown by Tanaka, who's the guy who invented monoliths, silica monoliths, that you can get 1 million plates out of a monolithic column, not easily, but you can get that, whereas getting any of the other columns to get 1 million plates, it gets to be somewhat problematic, real plates. Anyway, it's a nice way to compare, but it basically tells you that your sub-2 micron kind of peters out here. When you get to about 30,000 plates, you're in a faster time domain. So that's why you probably don't want to, if you want to get very difficult separations, you don't want to go. Now, I haven't talked about slip flow columns, but that's another domain too. Okay, peak capacity. How many peaks can you squeeze in a certain time frame? It's peak capacity. Calculate it. I'm going to skip this. This is the equation. It's pretty easy to calculate. But it's a way to measure the efficiency of a column under gradient elution. If you run gradients, you can't just calculate n because all the peaks have the same width and they're squeezed together. But it's a way to look at different particles. Here's 4 different particles, and then looking at the peak capacity using that calculation. You see that they're almost all about the same, where they're totally porous, superficially porous. Other work shows that it can be different. This is just another plot, some other studies that were done showing that this is totally porous 5 micron, 3 micron, and the purple is 1.8 microns. You see the blue is a 2.7 micron superficially porous, that the peak capacity in this particular case is about the same. The reason why the purple stops is this is a flow rate plot, peak capacity versus flow rate, is you run out of pressure, okay? So you can use the superficially porous well beyond the pressure of a totally porous. Sample capacity is another thing, that's loading capacity. Basically, if you go through the calculations and subtract out the solid core, the surface area of a SPP is about 75% of the surface of a totally porous particle. But because they're a different density, they pack differently, it's almost a wash when you actually do the studies. We've done some studies, or they've done studies, not we anymore. They've done studies at Agilent showing that when you start loading up a column, okay, there's totally porous columns here and there's superficially porous columns here. As you load more and more sample, eventually you start to oversaturate the column, and then you start losing efficiency, or the peak width gets broader. And when it falls about 10% of the peak of the efficiency, you call that the loading capacity. And you can see that most of them fall out about the same. So basically what I'm telling you is that the sample capacity of a totally porous or superficially porous are basically a wash. Same thing, this was basic. We did the same thing for acidic compounds, same way. Now, one thing that's kind of interesting is I mentioned that 2-micron frit. This comes into play when you work with really dirty samples and you don't want to go through all the filtering and the centrifugation and things like that. So we did some studies. We took plasma and precipitated the protein out. In order to get this kind of column lifetime out of a totally porous column, here's 2,300 injections, let's say, we had to go through and centrifuge and filter the sample through a 0.2 micron filter in order to get those kind of injections. For the superficially porous particle, on the other hand, we didn't have to centrifuge. We just did the precipitation, let it settle for about 10 minutes, and actually take a supernatant and inject it directly into the liquid chromatograph. And they seem to work pretty well. Monoliths are really good in this area, by the way. You can put on very dirty samples, straight plasma onto a monolith column and not plug it. So that's an advantage of monoliths that they don't talk about too much, but I think that's also a definite thing. This is just a T sample, the same thing. We've got 1,400 injections out of a brewed T sample without any filtration. So just to kind of summarize the column stuff, we looked at a lot of data, but pressure is half for superficially porous, efficiency about the same, pluggability is less with the superficially porous. The stationary phases are about equivalent now in terms of the number of them and different types. Particle sizes are becoming greater now on the SPP. So that's, I think, why the world is going over to superficially porous particles. And all the manufacturers, of course, are responding as such and coming out with their own versions of it. What I want to do in the last time I have left here is to talk now about the instrumental considerations. Most of those chromatograms that were shown in this previous part of my talk were all done on an optimized system. If you take a 20-year-old spectrophysics LC and you stick a little column in there like that, a 50-millimeter column, a 2.1 or a 4.6, you're not going to get those kind of separations. You're going to get blobs, and you're going to be very disappointed. And I remember walking into a pharmaceutical company in Southern California who had a mass spec, and they were wheeling the mass spec around to different LCs. And they were having problems with the short 50-millimeter columns, and they said, "What's wrong with this column? This column's crappy." And I said, "Maybe crap. This nice separations." Well, they had a 1 meter blue. If you know the Agilent code, blue is 0.25 millimeter ID. 1 meter of that connected from the mass spec to the column, and all they told them to do is change it to a 0.12, the regular red tubing, and it solved the whole problem just like that. So you could have the whole column optimized and the system optimized, but if you don't think about the other end, they can have it optimized in the ejection end by using tiny tubing, using certain injectors that have low needle volumes and so on. But if you forget about the other end or use a big detector cell, you're going to be in trouble. So what you have to worry about is, for the extra column volume, is the volume from the sample injection through the column, the infittings, through the loop, if you use a loop injector, through the infitting here, connecting tubing. All detectors have some internal tubing. The cell is not right there at the end of the detector, so you have internal, instead of the RI detectors, have fairly large internal volumes because they have to equilibrate the temperature of the sample coming in, and then you detect a flow cell. So you've got to minimize all those volumes, and that's what's been done on some of the newer types of LC systems that are out in the market. The other thing you have to worry about is what's called the dwell volume. Some people call it the gradient delay volume. And that's volume from the point of mixing of your two solvents, let's say A and B, through the pump in the case of low pressure mixing, through the pulse dampener, through the mixer, through these tubings, if you have an inline filter, through that, through the injection valve, through the loop, through the connecting tube, your column, to the first infitting in the column, that the gradient doesn't reach that point until it's traversed this entire volume. In older LCs, that can be as much as 2 to 4 milliliters. Now, these new LCs, using all sorts of fancy mixers and different type of tubing, smaller tubing, 0.075 millimeter tubing, and so on, they've really done a good job at minimizing the gradient delay volume. Because if you're trying to do a 2-minute separation, it takes you 4 minutes to flush out your gradient out of your tubing, you're not going to be able to do it, right? Unless you use some fancy things like isocratic holds and things like that. But if you just want to use it like a regular LC, you're not going to be able to do it if you don't have an optimized system for these tiny little columns. So dwell volume is easy to measure. You just make a change back at your, right here. This is where your gradient, when you read out your gradient, it's right here. It's not up here, okay? So that's why binary pumps are favored, because with quaternary pumps, for example, you have 4 solvents here. You not only have to go through all the tubing and stuff here, but you have to go through the pump chamber, that's volume, through the outlet check valves, the inlet check valves, all that stuff has lots of volume in it. So that's why most companies now who are selling all UHPLC systems kind of push the binary type of gradient systems, because it's a lot less of a delay volume. This is just an example. Just had to show you something here of Agilent. Otherwise, the instrument people will jump on me. But this is a new type of flow cell that basically has really a very small volume. I had it marked in there, I thought, but it's like 4 microliters square variance from that particular flow cell. It uses internal reflection. Oh, there it is. Yeah, 4 microliters of dispersion volume. And it kind of fits in there like that. So the sample comes in here. It's got a low dead volume tubing here, low dead volume tubing on the way out. And that minimizes. One thing they've done a really nice job on is this jet weaver mixer. It used to be, you need a lot of volume usually to do mixing. The mixers used to be 400 microliters, 2 milliliters. This is only 35 microliters, and it uses sort of a microfluidics design by some highfalutin engineers. Came up with this idea, and it really does a very good job of mixing in a very small volume. Some work was done by Guillochon and Sanchez and Farkas from Phenomenics. Am I over now? I am over. Okay, I'm almost done. Where they took standard LCs, and of course the 1100 was an LC that's been around for 10, 15 years, and they optimized the LC, and they did a really nice study showing by changing over some of the tubing IDs, by changing over some of the autosampler needle seat volumes and stuff, you can actually take a lot of dead volume out of these systems, okay? And in fact, the optimized Legend 1290, which is not on here because they didn't have it then, even the standard was pretty good. These are all good systems here, but they were able to eliminate even more volume by not only changing over the tubing and some of these other parameters, but by rearranging how the modules are stacked. Oftentimes you like to put the pump on the bottom because it's so damn heavy, you can't put it up on the top because it would weigh. Well, we came up with a rack that will actually allow you to put the pump on top. So then you can minimize these lines here that you have to do in order to recognize the efficiency of one of those UHPLC systems. So this just shows, the default 1290, the optimized 1290. To naked eye, it looks the same, but if you really do the calculations, and you can see the peaks are higher here, you basically only have 3.9 microliters extra column volume in that optimized system. That's the kind of volume you need to really do these highfalutin, high efficiency experiments. You really gain, this is isocratic on the optimized system, but you gain quite a bit in terms of efficiency and resolution. Less in resolution because it is square root of n, but you do gain by going to these minimal dead volume or systems. And you got to make sure that you optimize your data rate. This is an older slide, but now Agilent has one that goes on the diode array 160 hertz, which can handle almost any peak you'd run into. I won't go through this. This is basically what I've just said about the extra column effects, gradient delay volume, data rate, and so on. One thing that you can gain on, and this was shown in that paper that Guillochon and Gritty did with Phenomenex, is that you can use a weak solvent like water and actually take care of all the front-end extra column effects, because water is a very weak solvent in reverse phase. So if you can inject your sample in pure water or a very low % B, you're going to gain a lot of efficiency just in that alone. I'd like to thank the Agilent people who worked on these porous shell project, to these two people, app chemists at Agilent that supplied some of the data, to Desmond and his grad student, to Karen Cabrera from Merck, and to Guillochon Gritty, and the students who really did a lot to help Agilent improve the LC system by giving us feedback on performance of the newer instruments. And that's it. Sorry I ran over. Yes. Actually, the prep columns make it easier because you have a much larger volume. I think it has a lot to do with the cost of some of these newer packings. Prep columns still are traditionally 5 microns, 10 microns. If you load up a 10 millimeter by 30 centimeter column with these superficially porous particles, you couldn't afford to buy it. That's not quite true, but but they're more expensive.
Thank you.